I am building a regression model for a combined cycle power plant. The goal is to predict PE, which is the net hourly electrical energy output, from 4 environmental sensor readings: ambient temperature, exhaust vacuum, ambient pressure, and relative humidity. The data source has 9,568 hourly readings, so this is a supervised learning problem with a numeric target. The main metric is mean absolute error, because it is easy to explain. On average, how many megawatts are we off? Here is the modeling workflow. I use all 4 features, split the data into 80% training and 20% test, and keep the test set untouched until the end. Inside the training set, I use 5-fold cross-validation to compare models. The baseline is multiple linear regression. I also test polynomial regression and tree-based models. The simplifying insight is that random forest can capture nonlinear interactions between temperature, pressure, vacuum, and humidity without manually engineering every interaction term. The model comparison shows why random forest is the best choice for this demo. Linear regression gives a cross-validation MA of about 3.63 megawatts. Polynomial regression improves that to 3.36. Gradient boosting reaches 2.97, and random forest gets the lowest validation error at 2.51. After training random forest on the full training set, the final test performance is strong. MA is 2.39 megawatts, RMSE is 3.29, and R squared is 0.963. This is the required quick demo screenshot of the final model I created in Python. The script loads the CSV, selects IT, V, AP, and RH as features, and uses PE as the target. Then it performs the same 80-20 train test split and creates the final random forest regressor with 150 trees, max depth 14, minimum leaf size 2, and random state 42. After fitting the model, it predicts on the held-out test set. The terminal output shows the actual model object, the train and test row counts, and the same final metrics used in the deck. Test MA of 2.39 megawatts and R squared of 0.963. For the user experience, imagine a power plant operator dashboard. The operator enters current sensor readings, or the values arrive automatically from an API. The dashboard shows a predicted energy output, a scenario band, and a why this prediction view using feature importance. Temperature dominates this model, followed by exhaust vacuum, pressure, and humidity. The feedback loop is important. When actual PE becomes available, the system logs the error and can retrain on a weekly schedule. On privacy, this data does not contain personal information like names or health records, but if the system is deployed across multiple plants, locations and output patterns can reveal proprietary operational secrets. So the system should anonymize plant identifiers, encrypt predictions in transit, and restrict access to authorized operators. GDPR may apply if European operations or linkable location data are involved, and trade secret rules matter because the predictions reveal sensitive business performance. The ethical risks are mostly reliability risks. Temporal bias means a model trained mostly on summer data may fail in winter. Sensor bias means a faulty humidity or pressure sensor can skew predictions. Operational bias means the model may be weaker at low load ranges if there is less training data. The controls are performance audits by season and load band, sensor drift monitoring, prediction logs with model version, and a simple model facts label. To recap, regression task, MA metric, 80-20 split, 5-fold cross-validation, random forest wins, and final test MA is 2.39 megawatts.